Hi everybody. Today we're going to talk about the Milky Way. The Milky Way has been our constant companion in the sky. It used to be more visible when light pollution was not as common. This beautiful picture of the Milky Way was taken from Death Valley in Nevada, one of the darkest places in the United States right now. But today, you can still find a dark spot near Tucson and see the splendor of the Milky Way on a summer's night. If you take the time to find a very dark site, and let your eyes adjust to the darkness for 15 minutes or so, you will see a glowing band crossing the sky with dark lanes going across it. In some places, the skies are so dark that the Milky Way is bright enough to navigate by. And in fact, researchers in South Africa discovered recently that dung beetles, these friendly little animals over here, use the Milky Way at night to help them navigate to and from the nearest piles of dung. Ancient cultures thought of the Milky Way as just another object or pattern in the sky, like the constellations, adorning the celestial sphere for our nightly viewing pleasure. But we've seen in previous lectures that our cosmological view has evolved since then. The Earth was demoted by Copernicus to just another planet orbiting the Sun, and Galileo's telescope, pointed toward the Milky Way, was able to show that the faint luminosity spilling across the sky was in fact formed by many, many faint stars. But what were these stars? How big were they? How bright? How hot? None of this was known to scientists at this time because of one crucial problem. No one knew how far away the stars were. Without distances, it was impossible to tell how luminous these stars really were. And in fact, it wasn't until the 1600s that the notion that these stars in the sky could in fact be other suns just like our own emerged. Stellar distances are extremely hard to measure. Huygens, a Dutch astronomer, calculated just how far Sirius would have to be if in fact it was as bright as our sun, by using your by now well-known and loved inverse square law. The brightness and the luminosity are related by this equation here, and if you know both brightness and luminosity, then you can just solve for the distance. So what Huygens did was assume that the luminosity of Sirius was the same as the luminosity of the Sun, and measure its brightness, or the relative brightness between Sirius and the Sun, and therefore measure how much further Sirius was than the Sun, and he came up with a factor of about 30,000 times the distance to the Sun. That distance is almost too large to contemplate, and it was larger than anything that anyone had encountered before. But in fact, it would be another 200 years before we had the technology to allow the first distance to a star to be accurately measured. Check your understanding here. Today, we know that Sirius is an A star, and therefore much more luminous than the Sun. It's about 25 times more luminous. Was Huygens' calculation an underestimate or an overestimate of the true distance? Even without knowing the distances to the stars, we can still deduce a few things about the galaxy we live in just by looking up at the night sky. Ever since Galileo resolved the Milky Way into millions of separate stars, that astronomers have known that stars are not uniformly distributed on the sky. The narrow band of the Milky Way essentially circles us all around, under perfect conditions, with no moon and no artificial lights of any kind. You'll see that the Milky Way band reaches from one horizon to the other, dividing the sky in two. There are many more stars in the direction of the Milky Way than in other directions. If you think about it, that already tells us that the galaxy cannot be spherical. If you were living in the middle of a spherical distribution of stars, then the number of stars in every direction would be approximately constant. Instead, we must be living in something like a flattened pancake. When looking along the batter, all you see is more and more batter, Whereas if you looked up along the vertical axis, if the batter is thin, you'll see a few stars and then nothing. You'll be looking out into space, leaving your batter behind, or your galaxy behind, I should say. And this is just showing you that if you look in different directions, you'll see very few stars, and only along the direction of the Milky Way will you see the biggest and very much larger number of stars. But so we can conclude that we live inside a disk of stars. But where? Do we live on the edge? Do we live towards the center? You can reason that if we lived right at the center of the disk of stars, the number of stars along both directions of along the directions of the Milky Way would be the same. If we live towards the edge of the disk, then some directions along the Milky Way will have more stars than others. So William and Carolyn Herschel in 1790 tried to do this measurement more quantitatively. They did star counts. They essentially counted stars along all these different directions in the sky. And they found that although the number of stars quickly goes down when you look away from the Milky Way, any direction along the Milky Way, the number of stars was approximately constant. So they deduced that the galaxy was a thin disk and that the sun was close to the center. Because they did not know how far away any of the stars were, they can't place a scale on this system, so they don't know how big the galaxy is. They just know more or less what its shape would be. And even though they got the fact that the Milky Way is a disk right, they got the location of the sun wrong. We are not, in fact, anywhere near the center of our galaxy. But to understand why that is, we need to talk about what the galaxy is made of. These dark lanes that appear in the Milky Way, they look like empty sky, but what you're in fact looking at are regions of the galaxy obscured by dust. Those solid particles that are almost opaque to visible light and block our view of things behind them. The Milky Way isn't just made of stars. It has dust, it has gas to form new stars, etc. We'll talk about that etc. in the next lecture. If you look at the Milky Way in visible light, so the light that our eyes can see, the view towards the center of the galaxy is obscured by this dust. If we now look at the Milky Way in infrared wavelengths, you see that the center, the plane of the Milky Way where the disk is, becomes extremely bright. That's because dust absorbs light in the visible wavelength and re-radiates it in the infrared. What is this weird blue light that sort of forms an S shape around the plane of the galaxy? That's actually just a projection of zodiacal light, the dust in our own solar system. Remember, when we were talking about the formation of stars and planets around them, that stars form with these disks, these dusty disks that surround the stars, and that's the disks from which planets eventually form. Some little tiny dust particles of that disk still remain today in the solar system plane, and we can see them radiate in the infrared when we take this type of picture. Fortunately, because the dust particles in our solar system are a little bit warmer than the dust that permeates the galaxy, they radiate at a different wavelength. So you see that slightly shorter wavelengths, and that's why it's represented here in bluer colors, even though, of course, all of this light is at a wavelength that we can't actually see. But so because it comes out in a different wavelength, we can actually just filter that out and remove it from our image. And we're left with an image of the dust in the plane of the galaxy. That dust is absorbing and scattering the visible light, and therefore makes things fainter in the visible light. And that's what we call the process of extinction. Sources behind thick amounts of dust will look extincted. They'll look fainter than they would if there were no dust in front of them. Another thing that dust does is it absorbs and scatters more at shorter wavelengths, so that when you look at the objects, they appear to be reddened. They appear to be redder than they actually are, because the shorter wavelength light, the bluer light, is actually absorbed more. For these reasons, when you count stars in the plane of the Milky Way, you can't get very far because faraway stars are going to be heavily extincted by dust, and so they're so faint that you can barely see them. And that's why the Herschels got it wrong. It's true that the sun lives inside the disk, but not at the center, where we are in fact in the outskirts of the galaxy. So, because of dusts, it's really hard to measure how far out we must be, how big the galaxy is overall, how far does it extend. In other words, what is the scale of the galaxy? In order to do that, we must start measuring distances to stars. Once we can figure out what the average distance is between stars, then we can figure out how big the galaxy must be. It wasn't until the first parallax of a star was measured in 1838 by Friedrich Bessel that it was finally understood just how vast the galaxy might be. Remember, parallax is the apparent motion of a nearby star against further background stars due to the motion of the Earth in its orbit. As the Earth orbits around the Sun, our viewing angle changes, and the star appears to move against the background stars. Now, for a star like Proxima Centauri, would you expect the parallax angle to be the largest angle that we've measured from Earth, or the smallest? The nearest star to the Sun, Proxima Centauri, will have the largest parallax. Parallax is equal to 0.75 arcseconds. It'll have the largest parallax because the angle that the Earth makes with the star will be the largest when the star is the closest to the Sun and Earth. As the star moves further and further away, that angle becomes smaller and smaller so that the apparent motion becomes smaller and smaller. So 0.75 arcseconds is the largest parallax that we will ever measure from the Earth for a star, and that is not a very large number. Let me remind you that arcseconds are tiny, tiny things. So if you have a circle, you have 360 degrees in that circle. And so if I tried to represent a degree here, it looks really small. So let me blow that up. So that's what a degree looks like, 360 degrees of them in one circle. But now each degree has 60 arc minutes, and each arc minute has 60 arc seconds. So that means that in 1 degree you have 3,600 arc seconds, or that 1 arc second is 1/3600th of a degree. So remember that the full moon is about half a degree on the sky, so that's about 3,600 arc seconds divided by 2, or 1,800 arc seconds. So in order to visualize what an arc second is, you have to divide the size of the full moon on the sky into 1,800 little bits, and that's going to be the size of 1 arc second. Another way to visualize this is that 1 arc second is the size of a penny from 3 miles away. So that's really, really small. So if Proxima Centauri is moving a little bit under 1 arc second every year, you're trying to measure a motion that's 1/800th of the size of the full moon throughout the year. Why is this hard to do? I mean, it sounds hard, but why is it really hard? It's really hard because the atmosphere blurs everything, right? So any observation we do from the surface of the Earth of a star is going to be blurry. And to help you visualize this, these are pictures taken of a star, but they're really, really short exposures. They're only 1/100th of a second long, and they were taken all within the same second. So in 1 second, all of these images were taken of the star, but each one of them was only exposed for 1/100th of a second, and that really allows you to see the motion of the starlight on your detector, or on your camera, caused by those atmospheric turbulence, those molecular motions in the atmosphere. So molecular motions in the atmosphere tend to blur images. If we were to stack all these images together in order to make one integrated image over 1 second, the star would appear as a disk, and that disk is about half to 2 arcseconds in width, depending on how turbulent the atmosphere is on that particular night, and also how high up you are. The reason why we put telescopes at the top of high mountains is that from the top of a high mountain, you'll have to look through less atmosphere, and so these disturbances will be reduced. So on the surface of the Earth, there's sort of a hard limit to what you can do in terms of resolution because the atmosphere is just blurring everything. I mean, there are techniques in order to compensate for that blurring, but those have only been developed in the last 20 years or so. And in general, the best way to get sub-arcsecond resolutions is to go into space. Once you're above the Earth's atmosphere, the atmosphere is no longer blurring your images, and so the only thing that's setting the limit to how finely resolved you can make things is just your telescope and your camera. So you need a big telescope to increase your resolution, but you also need a high resolution camera with many, many pixels in order to capture the fine differences at very small scales. So this is what we did in the 90s with the Hipparcos satellite. This was the first telescope in space dedicated to measuring positions of stars very, very accurately in order to measure parallaxes or distances to stars. And before Hipparcos was launched, we only knew the distance to about 100 stars through parallax from the ground. With Hipparcos, that changed so that we were actually able to measure distances to hundreds of thousands of stars through parallax. So if Hipparcos can measure parallax angles down to 1/1000th of an arcsecond, so 0.001 arcseconds, which is a really, really small scale, then how much farther than Proxima Centauri can it measure distances? How much farther can we go with Hipparcos? Remember that the parallax for Proxima Centauri is 0.7 arcseconds. So the thing to remember is that the distance is equal to the inverse of the parallax angle, so distance equals 1 over parallax, so that if the parallax angle goes down from 0.7 to 0.001, or by a factor of 700, then the distance that we can go to will increase by a factor of 700. So we can go 700 times farther than the nearest star, and that's a fabulous achievement. It allows us to measure the distances, like I said, to 100,000 stars. But it only takes us so far. Beyond that, parallaxes are at the moment too small to measure. So again, the maximum distance for Hipparcos will be 700 times the 4.3 light years to Proxima Centauri, so only about 3,000 light years away. We're at a very exciting point in time right now because just in December of last year, Gaia, the new parallax satellite, if you will, from the European Space Agency was launched. And Gaia will be able to measure parallax angles of 0.00002 arcseconds. So again, this is another factor of 50 improvement in the parallax angle that you can measure, which translates to another factor of 50 in distance. Gaia does this by having a larger mirror, so a larger telescope, but also by having an incredibly high-resolution camera. It's now a gigapixel camera, so compare that to your megapixels in your digital cameras. This is a gigapixel camera and is able to see parallax angles, again, of 2 micro arcseconds. So a factor of 50 in distance doesn't seem that big, but if we look at this to scale, so here we are, there's our galaxy, and we're out in the periphery of the galaxy, where that arrow points us, and we're right in the middle of the disk. So Hipparchus, the previous satellite, the information that we have right now, only takes us to that radius that's signaled here. But if you increase that by a factor of 50, as Gaia will do in the next few years, that's where we can go. So that really allows us to probe a much, much larger region of the galaxy, and in fact, it takes us all the way to the center of the galaxy, which is great. So that's happening right now. Gaia has reached its orbit, its position in its orbit, and is currently taking commissioning data, so it's being tested to make sure that it's working properly before it starts its official survey mode in May, so that's just next month. And then it's going to start measuring these tiny little changes in positions of stars. Remember, to the milli-arcsecond, to the micro-arcsecond, excuse me, and thereby measuring distances out to almost half the scale of the galaxy. Beyond this limit, stars' motions will again be too small to detect, and we can no longer tell their distance. We're making great progress measuring smaller and smaller parallaxes, but even Gaia will not take us to the other side of the Milky Way. And so if we want to go further than that, if we want to measure the whole galaxy, or even things that are beyond our own galaxy, we're going to need a different method to measure distances. Parallaxes that small are just impossible to measure in the near future. So we're going to need another method to go farther. And in order to do that, we're going to again use our well-known and loved brightness-luminosity relationship, or the inverse square brightness law, because by knowing the luminosity and the brightness, you can measure the distance. So for most objects, we don't know how intrinsically luminous they are. If we were to use a light bulb, we do know how intrinsically luminous it is. It says it's 100 watts. The bulb says 100 watts, so you know that it's always putting out 100 watts of luminosity. So you could place this bulb at any distance and measure how bright it appears to you, and from that measurement, from the apparent brightness and knowing its intrinsic luminosity of 100 watts, you could calculate its distance at any distance. So a 100-watt bulb is what we call a standard candle. It's a source of light for which we know what its intrinsic luminosity is. And what we need in astronomy is astronomical standard candles, objects for which we know how intrinsically luminous they are, so that when we observe them and we measure their apparent brightness, we can deduce how far away they are. And this story in astronomy was again done by a very important woman. The Henrietta Swan Leavitt was the woman who figured out how and what we were going to use as standard candles. And she did so when she was working, again, she was one of the Harvard computers, and she was analyzing photographic plates of the Magellanic Clouds. The Magellanic Clouds are two sort of faint cloudy smudges in the southern sky. And she was looking at photographs of these plates, and she noticed that some of the stars in those clouds appeared to vary in brightness. So she measured the brightness of those stars in different plates that were taken at different times, and she deduced that the brightness of these stars was varying periodically, which meant that at some point they were brighter, their brightness diminished, and then it shot back up, and then it diminished again, and then it shot back up. And it did so periodically so that you could measure a period of these variations. And what she found was that there are many such stars in the Magellanic Cloud. So here's another picture of one of the large Magellanic Cloud, and you can see that it's filled with stars, and a few of those stars will vary in this very periodic way. And what she did was she plotted the period of the star here on the x-axis. This is the plot that she made. On the x-axis, you have the period, or the logarithm of the period. That's just a mathematical function. And then on the y-axis, she's measuring their apparent brightness, so the brightness of the star. And she takes the brightness to be sort of the peak brightness. And she sees that there's a very tight correlation between the period and the brightness of each star. Now, because all of these stars are located in the Large Magellanic Cloud, she was able to assume that their distances are all the same. And if the distance d is the same, then you know that the brighter the star, the more luminous it is. So brightness and luminosity are just directly related. So what she was in fact measuring for all of these stars in the Large Magellanic Cloud was a period luminosity relationship. So once you know the period of a star, of one of these stars, you can deduce how luminous it'll be. Now, because she didn't know what the distance to any of these stars were, she needed to calibrate the period luminosity relationship in order to actually be able to use it. And actually the person to do this is a very hard thing to do, because these stars, these variable stars, there aren't any of them that are close enough to the sun or to the earth in order for us to measure parallax for them. So it's really hard to actually get the distance to one of these stars precisely. The person to do this was Shapley a few years later. He was able to calibrate the period luminosity relationship so that now all we have to do is observe one of these stars and measure its period of its variability. So you would basically look at one of these stars over a period of 1 to 10 to 100 days, and you would see that the apparent brightness of the star varies in this very cyclical, periodic way. So then you measure what the period will be. For this particular star, that period is about 3 days. And then you look at the period luminosity relationship. So on the x-axis here, you have the period of the variability in days, and on the y-axis, you have what the intrinsic luminosity of one of those stars would be. So for this star, we measured a period of 3 days, and you can then find what the luminosity for that period of luminosity relationship should be. And there you have it, the intrinsic luminosity of this star. This figure shows you both Cepheids. These are these types of stars that have longer periods. And it also shows you these types of stars called RR Lyrae. These names come from the first star of their kind to be discovered. So there was a Cepheus star and an RR Lyrae star. And the thing to note here is that for Cepheids, the longer the periods, the larger the luminosity, so the brighter, the intrinsically brighter the star is. Whereas for RR Lyrae stars, they're actually all more or less the same intrinsic luminosity. So they're all equally luminous. So all you need to know is identify that they are RR Lyrae stars by their specific shape of their curves, and then you immediately know how luminous they will be. What Shapley also determined was that globular clusters have many of these variable stars called RR Lyrae. So this is a movie of the globular cluster M3. You might remember M3 from last week when we talked about globular clusters. This was also the same cluster that we observed during our star party. And by taking many pictures over the duration of one night, this observer was able to capture the variations in brightness of each one of these stars. It sort of looks like Christmas tree lights, right? It's really impressive. So these stars are varying with periods of less than a day. These stars vary in brightness because they're at the end of their life, and they've run out of fuel. They're trying to reestablish hydrostatic equilibrium, but the thermal pressure is out of sync with the gravitational compression. The expanding star overshoots the equilibrium point. Then gravity catches up and contracts the star. But gravity contracts the star beyond the equilibrium point. The thermal pressure increases too much, and the cycle continues. As the radius pulsates, the temperature also increases and decreases, which means that its intrinsic luminosity is also varying. It's quite the image to think about one of these giant stars changing so much in radius that its temperature and radius and luminosity can change so visibly in the course of a single day. So Shapley found these variable stars in all of these globular clusters, and because, again, by measuring their period, he can know how intrinsically luminous they are, then all he needs to do is measure their apparent brightness and obtain their distances. So he can measure distances to all these globular clusters, and he can establish the true size of the galaxy. So here's a picture of our galaxy. The sun is at the point with inside the disk, and the globular clusters are actually spread out all over inside what we call the halo of the galaxy. So they're not confined to the disk plane. But by measuring how far away all of these globular clusters are, that gives you the scale of the galaxy. And so Shapley determined the galaxy to be 100,000 light years in length. Notice that because these globular clusters are located outside the disk of the Milky Way, they are ideal to use as sort of markers for distance because they don't suffer as much from extinction as things that are located inside the disk of the Milky Way. So that's also why globular clusters are so important, because they actually serve as distance markers outside of the disk of the Milky Way. This is a picture of the Sombrero Galaxy, or M104, taken by Hubble, and this is a nearly edge-on galaxy that looks much like our own, and this gives you another perspective on how thin that disk is and how dusty it is. Look how dark those dust lanes are, and then how the whole disk is sort of inserted into this halo of stars that surrounds it, and so it's in that halo, that big spherical halo, that the globular clusters orbit, and that halo is formed by older stars that have been there for many billions of years. So here are some models for our galaxy. If we look at it sort of face on, it has this disk with spiral arms in it, and we live along one of those spiral arms in the outskirt of the galaxy. There's a bulge at the center, so a sort of spherical bulgy thing right at the center of the galaxy, and then there's a halo that surrounds the galaxy where the globular clusters live. If you were able to look at our galaxy edge-on, you would see, again, the disk of the galaxy, but now you would notice just how thin that disk is compared to the length or the width of it. So if the disk is 100,000 light years in diameter, it's only 1,000 light years thick, so that's 1/100th of the thickness, 1/100th of the width in the thickness of the disk. And for comparison, so that you can visualize just how thin these disks are, that's the exact same aspect ratio of a CD, a compact disk. So if you think about what a CD looks like and how thin it is, that's how thin the disk of our galaxy is. And again, you see the bulge at the center, and then the halo surrounding the galaxy with its globular clusters. We'll talk in the next lecture about the bulge and what lies at the very center of our galaxy, and also a little bit about the halo, a little bit more about the halo. And again, within this picture of our galaxy, our solar system is out here in the outskirts, nowhere in particular. So here's a summary of what we've talked about in this lecture. I'll leave you with this cartoon from Calvin and Hobbes and let you know that in the next lecture, we're going to be talking about first the contents of our Milky Way galaxy, and also how we might go about looking for distances to things that are outside of our own galaxy. In fact, for a long time, people weren't sure whether there was anything outside the galaxy or whether the galaxy was the universe. Now we know that galaxy and universe are very, very different things. And if you're impressed by the scales of our galaxy, you'll find the scales of the entire universe even more impressive.